In day 12, we're going to do all of our circle theorems, all of our circle definitions, all of our circle everything. Okay, those of you that took the course, you probably spent 2 to 3 weeks on this during the school year, if not longer. Um, those of you who have not, that means you're going to be doing a lot. You're going to be learning a lot. I'm going to be throwing a lot of formulas and definitions and theorems out at you in this lesson, but you're going to hopefully get it to sink in quickly. Notice I have 33 slides on this. I'm going to try to keep the video under 25 minutes. We'll do the best we can here. I'm going to go quickly through, especially the vocabulary. And some of it's repetitive. 33 slides, some of it is very repetitive. I just have everything in the packet in here. So we will go quickly. Make sure you take good notes. And and it really, a lot of this isn't as bad as it's not really that bad. So we can go quick through a lot of it. A lot of the math is quick. Okay, it's just a matter of knowing the relationships. So on page 1, read through vocabulary. Make sure you understand what all these are. Interior of a circle, inside the circle, exterior of a circle, outside the circle. A chord. Just going to draw a real quick chord for you. Actually, I'm not going to draw them because they're on the next page. So here's chord, secant, tangent, point of tangency. Uh, Congruent circles are circles that have the same radii. That's important. We'll talk about these concentric tangent circles and common tangent on the next page. There's actually drawings for you. Okay, so we're going to move on to here. Here's those definitions again, and here they are in picture form. Very, very important here. A chord is when the endpoints are on the circle and it goes through the middle, the internal of the circle. Okay, it's got to be inside the circle. A secant is like a chord, except it goes outside the circle, and it's a line. It's not a line segment. It goes outside the circle. But a secant and a chord, when you're inside the circle, pretty much have the same properties because you do kind of have a chord on the secant. You see that? And then a tangent is kind of, well, it's not like a secant because it only hits the circle once, but it does go outside the circle. That's why it's like a secant. So tangent and secant kind of go together, but a tangent line only hits the circle at one point, and that point is called the point of tangency. So very important diagram here for you. Concentric circles. Concentric circles are coplanar. That means they're in the same plane, and they have the same center. So I'm just going to draw an example of concentric circles. Here we go. The circles are concentric. Okay, they share the center. They have the same center point. And then tangent circles. There's 2 examples of tangent circles I can draw for you. You have what are called internally tangent and externally tangent. If circles are internally tangent, oh my goodness, bad circle. Anyways, they tangent means intersecting at one point. So think about that. 2 circles are inside of each other and intersecting at one point. So maybe something like this. Okay, you have that one point. You have that point of tangency right there. Hopefully your circles look better than mine. You have a circle and then another circle, and then you have the point of tangency. Externally tangent circle, this is internally tangent. Internally tangent. Okay, if they're externally tangent, you would have a circle, and then you'd have another circle. Oh boy. Pretend they touched. All right. And they pretend they touched at one point there, and that would be example of externally tangent. They intersect at one point. Okay, make sure you put externally tangent there. All right, so some theorems. Very important theorems here. These 2 kind of go together. They're basically saying the same thing, just they're backwards of each other, different conclusions. When you have a radius, look at the picture. The words are confusing. Just I'm trying to simplify it for you. When you have a radius, and it could be a diameter, it doesn't matter. If I extend this, it's the same thing, okay? So when you have at least a radius, and it intersects a tangent line, you always get a 90-degree angle there, which means that they're perpendicular. And I want you to add a conclusion here. Angle A, B, and then we'll just put a C here for the sake of naming it. Angle ABC is a right angle. And that just comes from being perpendicular. The theorem says that a radius to a tangent is perpendicular. That's the conclusion. And then this is just going backwards, basically. If you know they're perpendicular, then this must be the tangent. You see? If you know you have a 90-degree angle there, this must be the tangent. So basically the same thing. We're already on slide 5. We're moving along. Another very important theorem, if you have two tangents, these are two tangents. I'll call this tangent 1 and tangent 2. Notice how they only hit the circle one time. They only hit the circle at one point. They could continue. They could continue on. It doesn't matter. That doesn't matter. I'm talking about this tangent segment and this tangent segment. If they meet at an external point, they are congruent. That's the conclusion. So AB would be congruent to AC. Very, very simple. So if this is 10, this is 10. The tangent segments are congruent. Okay, I'm not reading the theorems because if I read the theorems word for word, it's just going to confuse you. Theorems word for word are very, very confusing. I'm just trying to give you the picture with the formula. If you can relate the picture to the formula, you're going to be fine. Now we get into more vocabulary. Central angle, arc, minor arc, major arc, semicircle, adjacent arcs, congruent arcs. Congruent arcs basically are arcs that, adjacent arcs really aren't that important. Congruent arcs equal arcs. Semicircle is 180 degrees. It's a half a circle. A central angle, I want to draw, do I have the drawing here? Kinda, but I'm going to draw a central angle for you. A central angle is when the angle is at the center point. So we have a center point, and then anywhere you want to draw the angle, but it's got to be at the center point. So say I do this here, then this angle right here would be a central angle. Okay, that would be a central angle. And then an arc, well, an arc is just a part of a circle. So like this right here is an arc. And you could draw, all the arcs add up to 360. So you can, if you just keep splitting the circle up, you just keep getting arcs. See that? Arc, 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 arc. All right. Now the difference between a minor arc and a major arc, let's say you have a central angle. Okay, here's my central angle. The central angle will have an arc. This is called an intercepted arc right here. This is called an intercepted arc. The intercepted arc is the minor arc. This would be a minor arc. And then you can go around the circle the other way. So you got these 2 points here. If you go the shortcut way, it's a minor arc. If you go the long way, it's a major arc. And a major arc is going to be greater than 180, and a minor arc is going to be less than 180. It's very simple because you have 360 degrees in the circle. All right, so some theorems here. These are pretty almost common sense theorems, I call them. Congruent central angles have congruent chords. So here, see the picture here? Congruent central angles. Look at what's given. I have congruent central angles. Therefore, I must have congruent chords. So I'm going to draw the chords in. I'm going to draw my chords in here. Okay. Right here and right here. All right. So that means DE is congruent to CB. DE is congruent to CB. And you can tell that it's almost obvious because this space is the same as this space. So why wouldn't this space be the same as that space there? The length there. Okay, so that kind of makes sense. Congruent chords have congruent arcs. That's just going backwards. So if I know the chords are congruent, I can say that the angles and that the arcs are congruent. Well, they're talking about the arcs here. So arc DE would be congruent to arc CB. See that? If the space here is congruent, the space to the and the arcs must be congruent. So DE, arc DE, see I put a little arc here, arc DE must be congruent to arc CB. And then congruent arcs have congruent central angles. So if I know that the arcs are congruent, see what's given here? I know the arcs are congruent. I can say the central angles are congruent. These two angles right here. So angle DAE is congruent to angle CAB. CAB. Okay, and those all kind of go hand in hand. Very, very simple. More more terminology. Inscribed angle. Now an inscribed angle, very important. An inscribed angle is not at the center point. You do have a center point, but the inscribed angle won't be at the center point. It'll be on the circle. It'll be on the circle, and then it's created by two chords. So say one chord does this, and another chord does that. See that? So it's created by two chords that intersect. Okay, two chords that intersect on the circle, obviously on the circle, make an intercepted arc. So there's my intercepted arc. I want you to label this diagram here. Intercepted angle, sorry. Wow, I'm using the wrong words. Inscribed angle. Okay, so this would be an inscribed angle right here. Okay, it's made by two chords. And when you have an inscribed angle, you get what's called an intercepted arc. And the intercepted arc is inside the angle, basically. So here's the angle, and here's the intercepted arc. Here is the intercepted arc. I want you to label that. Put endpoints even on it. This is called the intercepted arc. Okay? Subtend is an arc or a chord. It subtends an angle if the endpoints are on the sides of the angle. Okay, so this is the same. It's very similar to inscribed. They use subtending sometimes. All right, here's the inscribed angle theorem. Now we're going to actually get into measures. These are theorems that give us measures of angles and stuff, okay? The relationships, there's going to be diagrams with a formula. You're going to see diagrams with formulas for these, okay? These are all inscribed angles, three different types, okay? You can be inscribed through the center. You could be inscribed one on each side of the center. You could be inscribed both being on the center. If these aren't dark enough for you, I want you to darken them. By the way, I am on page 7 right now, okay? You might want to darken these because the photocopy didn't work very well. So we got AB and BC going right through the center point. That makes an inscribed angle. You got AB and BC, one on each side of the center point. That makes an inscribed angle. And then AB and BC on the same side of the center point, and that makes an inscribed angle. So there's a lot of ways to make inscribed angles. It doesn't matter. Any of these diagrams is going to follow this formula here, and it's a very simple formula. The angle, the inscribed angle, is half of the intercepted arc. So if this is 50, this is 25. It's very simple. If the arc is 50 degrees, the angle will be 25 degrees. Or whatever, okay, 50, 25, 50, 25. Say this is 40, then this angle will be 20. So it's a very simple theorem. All right, an inscribed angle subtends a semicircle if and only if it is a right angle. Well, that's because, let's draw a picture of this. You have a semicircle, right? And we're subtending, so we can make the point anywhere we want. And this is an example of subtending, okay, this angle right here would be subtending the circle. Well, if this is a semicircle, then the arc is 180 degrees, okay? And if the arc is 180 degrees, the angle must be 90 degrees because the angle, the inscribed angle, is half of the intercepted arc, you see? So this is 180, this must be 90, therefore it's a right angle. So that's that theorem explained to you. Here's a corollary that goes along. We're not going to really use this today. We're going to use it in proofs, so we're not really going to use it today. But if two inscribed angles intercept the same arc, then they are congruent. So take a look at the picture here. You got this angle intercepting DE, and you got angle B intercepting DE. So if angle A and angle B both intercept DE, they obviously have the same measure. If this is 70, then isn't this 35 and this 35? So if they're both 35, they're congruent. If I change this to 80, so what? 40, 40. Because they intercept the same arc, so they both have to be half of the arc. Therefore, they're congruent, so you get this conclusion right here. Again, we're not going to use that today, so I just kind of threw that in there because it kind of goes along with it. if this theorem's almost the same as the last one, let's say you have a chord or even a secant and then a tangent. So a secant and a tangent intersect. See how it's on the circle? This is how I always ask my students to remember it. If it's on the circle, it doesn't matter if it's inscribed or this situation. If the vertex is on the circle, it's going to, again, be half of the arc. So here's your arc AB. This angle here will be half of that arc. So if the vertex is on the circle, if the vertex is on the circle, write this down. If the vertex is on the circle, it's going to be half of the arc. The angle will be half of the arc. Okay? Now, these two are opposites of each other, kind of. The next two scenarios here. We have, oops, did I have the same slide twice? Okay, so whatever, we'll do this one. This one here is when you have two secants or chords, because it doesn't matter. See the situation here? They drew two chords, but does it really matter if I extend outside the circle? Because it doesn't change the angle measures in the middle. All right, if you have two chords, it creates these vertical angles here. You see that? Angle 1, and I'll just call this angle 2. Angle 1, angle 2 would be congruent. The way you would find these measures of these angles here is you do this. You do half of the sum of the arcs. So there's two intercepted arcs, AB and CD. You add those arcs and you take half. That will give you the angle in the middle. I know I'm throwing a lot at you here, and it's confusing until you actually see the examples. But once you practice it in class tomorrow, I think you'll really get the hang of it. All right, so we'll do examples of that later. Then you have an angle outside the circle. See how all these angles are outside of the circle? All right, when the angles are outside the circle, formed by secant and a tangent. This one's formed by a tangent and a tangent. This one's formed by a secant and a secant. It doesn't matter what it's formed by. If the angle is outside the circle, okay, then it's the same formula. See how they're all subtracted? You just subtract the intercepted arcs. You subtract the intercepted arcs. You subtract the intercepted arcs, and then you take half. And that will give you the outside angle. Again, I'm throwing a lot at you. I know it's hard, especially if you haven't seen this before, but we're going to do some examples coming up very soon here. Here's some examples already done for you, so you can take a look at those. I'm not going to bore you with that. Externally, here's some segment relationships and circles I'm going to go over with you. Externally, secant segment, tangent segments, okay? And we'll do those more in class tomorrow. All right, and here's some examples we're gonna do with segments. These are the lengths of the segments. Okay, we just talked about angles, and now we're talking about the lengths of the segments. And these are the last three formulas for the day, and then we're going to do some examples. So when you have two chords, these got to be chords, intersecting in the circle. Now this is not the center point. The center point's like right here. So this is not intersecting at the center point. What happens is you get four pieces. You get four pieces of the chord. This is the relationship. If you multiply the chord segments of each chord, they're equal to each other. So CE times ED is going to equal AE times EB. Okay, and again, we will be practicing this today. Secant product theorem. This is when you have two secants intersecting outside the circle. All right. If this is the case, what you do is you take the outside segment, BE, and you multiply it by the entire segment, not the inside segment, the entire segment, AE. And that's going to equal the outside segment, DE, times the whole segment, CE. Okay, it's not the inside. You don't use the inside segments. And why is that? Well, the reason is because it works. It works for every circle. If this wasn't a 25-day class, if this was a whole year, we would actually show how this works. Okay, but we don't have time for it. So I'm giving you the formula. You've learned, if you took the course before, you've done this. So it's just a matter of a refresher for you. And this one is actually the same thing. This is a secant and a tangent. So it's outside BC times the whole thing, AC. And this one is, the problem is we don't have an inside segment, but that's okay. The outside segment is CD times the whole segment. Well, the whole segment is again CD. So it's outside times whole equals outside times whole. Got to remember that. Outside times whole equals outside times whole. So what we do here to shorten it, the way you'll see this theorem is BC times AC equals CD squared, because there's CD, the outside is the whole segment when you have a tangent. All right, so it's CD squared. All right, we're on slide 21. We're getting there. Here's some examples already done for you. If this was given, 3 times 8 equals 4 times 6. 24 equals 24. That's a check. All right. 8 times 6, because the whole thing is 8 and the outside is 6. So that's 48. And then the whole thing is 12 and the outside is 4. So 12 times 4, which is 48. You could see how that works. And then this one, the whole thing, the whole piece is 9, 5 plus 4, and the outside's 4. 9 times 4 is 36, and then the outside and the whole is 6. 6 squared is 36. So you can see how this checks out. All right, we're going to roll through these examples and we will be done. The examples go quick, don't worry. Angle PRU. PRU, that's this angle right here. That is an inscribed angle. Write this down. That is an inscribed angle. Inscribed angles are half of the intercepted arcs. Oh, I did a little bit too much here. I just want this angle here. PRU, okay? This angle is half of its intercepted arc. Here is my intercepted arc. It is 118. So it's going to equal 1/2 of 118, and that is going to be 59 degrees. And that's it. Arc SP. Well, arc SP is right here. It is an intercepted arc, so it's double the inscribed angle. So here's my inscribed angle, 27. So I'm going to do 2 times 27 because I'm going backwards. You double the angle if you want the arc. So that's 54 degrees. All right. So I told you to go quick. We are on A. All right. This time we got to look at the relationship here. Here is the thing that has A in it, and it's this angle right here. Well, we talked about if you have, this is 180 degrees here. The arc is a 180 because you could tell it's a half a circle. So then the inscribed angle is going to be 90. So 5A plus 20 must equal 90. And that's going to be our equation. So 5A equals 70, and then A must equal 10.5. You just divide that out, divide by 5. That's it. All right. This one here, I said we wouldn't be using this today, but I lied. Angle J and angle K. They both are inscribed angles because they're on the circle. See how they're on the circle? So they're inscribed. And they both intercept LM. They both go to L and M. See that? They both intercept the same arc. If they both intercept the same arc, they must be congruent. So we're going to say 5B minus 7 equals 3B. And then we're just going to solve. We're going to subtract 5B. Negative 7 equals negative 2B. Divide by negative 2. So B equals 3.5. And then they want you to find LJM. LJM is this one right here. So we're going to do 5 times 3.5 minus 7. And that is going to be, I have it on my paper here, 10.5. 10.5. Okay. Oh, I actually messed this one up. This one actually was 14. I just looked at my paper without actually, wow. 70 divided by 5, 10.5. Okay, Mr. Ventry, you are messed up. All right, obviously 70 divided by 5 is 14. Next time, just do the math instead of using your paper. Okay, so here is, this one was 10.5. Sorry about that. All right, example 3. Now we have congruent chords. Look at this. Look at the given information. We have congruent chords, and we learned that congruent chords intercept congruent arcs. So these arcs must be congruent. 9n minus 11 equals 7n plus 11. There's our equation. You got to set up an equation based on the relationship. Move this over here, you get 2n, add 11, you get 22. N equals 11. Find WS. WS is this. 7 times 11 plus 11 is going to be 88. That's our final answer. And again, feel free to try these without the video. This one, these are two tangents that come together at an external point. The theorem is that they are congruent. Go back and look at the theorem if you need to. 4 plus 2a equals 5a minus 32. Bring the 2a over, add the 32. 36 equals 3a, a equals 12. Is that what they wanted? No, they want HG. Make sure you answer the question. HG is right here. 4 plus 2 times a is 12. 4 plus 2a, see that? So 4 plus 24 is going to be 28. So HG is 28. Moving along. This one here, you have 8 and 9 here. Now the theorem is that this is the radius bisects the chord. So it cuts the chord into 2 equal pieces. So we can call them both x. All right, we can call those both x. The other thing we could do is, this is where you got to get a little creative. The radius of this circle, excuse me, is 17, 8 plus 9. So what I want to do is draw another radius, because that gives us another side. Draw that radius right there. Label it 17. If this is 17, then this must be 17. Now what you've done is you've created a right triangle. Okay, I have x, because I don't know what this is. I know this is 8. This piece is 8, and I know this is 17. So now what you can do is the Pythagorean theorem, because it's a right triangle. So you can do x squared plus 8 squared equals 17 squared. X squared plus 64 equals 289. X squared equals 225. And so we're going to get the square root, which x equals 15. Okay, so 15 is x. So the whole, we wanted NP. Well, if this is 15, that means this is 15, and 15 plus 15 gives us 30. So NP is going to be 30. All right, so that one you had to get a little creative on. Right here, I'm going to omit B. We're just going to do A. We're not going to do B. EFH, EFH. That's one of those angles that's on the circle again. It's formed by a tangent and a secant. So it's just going to be half of the intercepted arc. There's my intercepted arc, 130. So I'm just going to do half of 130. So we're back to the easy ones, which is 65. We have this one. All right, now we're going to do inside the circle and outside the circle angles. Angle AEB right here. That's inside the circle. It's equal to this angle. So whatever this one is, this one is. But notice how you have two intercepted arcs for those angles. You have this intercepted arc, and you have this intercepted arc. And the formula is, for an interior angle, it's 1/2 the sum. It's 1/2 arc 1 plus arc 2. The sum of the intercepted arcs. So it's going to be 1/2 of 139 degrees plus 113 degrees. So it's 1/2 of 252. and that's going to give us 126. So both of these angles are 126, which is what we wanted to find. We wanted angle AEB, so 126. All right, a couple more here. Now the angle's outside the circle. Notice that this little angle here is outside the circle. So we're going to do, x is going to be 1/2 of the difference in the intercepted arcs. So here's arc 1, 87. And here's arc 2. This little one here is 7. I know the picture's not great. So it's 1/2 of 80, which is 40 degrees. And then this one here, again, it's outside, so it's going to be half of the intercepted arcs. So x is going to be 1/2 of 200 minus 74. And these will get a little more challenging in class tomorrow. It's not going to always be this easy. Those of you that took the course know there's other ways they can ask these. And this is going to give you 63. All right? 3 more examples here. We're done. Now the segment examples here, okay? So they give you 3 of them, and you got to find the last one. The relationship is that GJ times JH is going to equal FJ times J8 times JE. 14 times X. So this piece times this piece. There's the center. I mean, not the center. There's the intersection point. It's going to equal this piece times this piece. So it's going to equal 7 times 10. 14x equals 70, and we know from before that 14 goes into 75 times. Oops, 14x. X equals 5. So that is what they wanted, so that is done. 2 more. Now we have 2 secants. So we have the outside piece times the whole piece. The outside piece times the whole piece. So it's going to be 8 times the whole piece, which is x plus 8. The whole piece is x plus 8. And then outside, which is 7, times the whole thing, which is 16. 9 plus 7. Okay? So we get 8x plus 64 when you distribute equals 7 times 16, which is 7 times 16, which is 112, if I'm not mistaken. And then subtract 64. 8x equals, I'll just pull my calculator out here for you. And 64, we shouldn't need a calculator, but my brain's fried right now. X equals 6. Okay, and that's what you should get. X equals 6. Last one. This is a secant and a tangent. Same formula though. Outside times the whole thing, 20, equals the outside times the whole thing. Well, they're both x, so x squared. So this is 100 equals x squared, and then we take the square root, and we get 10. Hopefully you were able to follow all that, and I will see you in class tomorrow.